In our previous video, we came across some alternate definitions of sine, cosine, and tangent as defining them as ratios inside a right triangle. And let's just first maybe talk about a little bit about a right triangle. Let's go ahead and assume that these are right triangles here. And there we go. We'll assume that the right angle is down there in that corner for this particular triangle on the left. And our naming convention is we typically label the angles with capital letters. We'll call them A, B, and C here. And then we label the sides using lowercase letters, and we do it opposite the angle. So if the angle A is down here on the lower right-hand side, all right. If the angle is down here on the lower right-hand side, then the side A would be the side that's opposite that. If B is the angle in the top left, then in the lower sort of right side would be B. And if angle C, in this case, I've got it labeled as the right angle, then the hypotenuse would be side C. And you'll notice that I'll use a script C when I'm doing things by hand, because when you're handwriting, it's hard to tell the difference between a lowercase c and an uppercase C in there. If I have my triangle over here, and I'm going to assume that that's the right angle, let's call it W, and then the side opposite that would be a lowercase w. Uh-oh, big W and little w look a lot alike as well. So I don't know what I'm going to do about that. Maybe I'll add some feet or something on the uppercase W. And if I have capital R as that angle, and then the opposite side would be little lower r opposite that angle. And if I have another angle down here on the bottom right, and how about a capital T, and then it would be a lowercase t on the side opposite that. But what we want to do is we can use trigonometry. If we're given any one side, we should be able to find, and one angle, we should be able to find the values of all the other pieces in that triangle. So let's suppose that here in this first angle, I'm given that angle A is, let's say that this is something like um, 32 degrees. And let's suppose that we're given side B as, let's make it 18 or something like that. And the goal is to try to find all the other values for our triangles. Well, we know that if I stay with 32 degrees, I know that the tangent of A is, well, what sides do I have? Well, A over here would be the opposite side. Little a is the opposite side. And then with B, if I'm working with the angle B, side B is the adjacent. And we've got C here as the hypotenuse. So if I want to take an angle that involves, if I want to find side A, I see that's the opposite side, and I've got the adjacent side there. And so I know that the tangent ratio relates the opposite and the adjacent things. Remember, it was SOH, CAH, TOA, that the sine of an angle, sine of the theta, was the opposite side divided by the hypotenuse. The cosine of theta is the adjacent side divided by the hypotenuse, and that the tangent of theta is the opposite over the adjacent, where our relationship's in there. So, SOHCAHTOA is what that's sometimes referred to, that the sine is the opposite of the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is opposite over the adjacent in there. And so if I'm looking here for side A, that's the opposite side, and I know the adjacent side, so I'm going to choose the adjacent of the tangent function. I know that the tangent of 32 degrees would equal, the opposite side would equal A divided by 18. A divided by B gives us the tangent, the opposite for angle A. The opposite side is A, the adjacent side is B. Not the hypotenuse, though. The hypotenuse is also sort of adjacent to A, but it's the hypotenuse. It's not the A value, the adjacent side. But that gives us an equation that I can solve for A. I can just multiply both sides of this equation by 18. I'll switch color here to say that I'm doing something. If I multiply both sides by 18, I'll end up with A is equal to 18 times the tangent of 32 degrees. And then I can go to my calculator and I can get that value here. I think I've got Desmos. Yep, there's Desmos pulled up on my calculator. Make sure that we're here in degree mode. And if I just do 18 times the tangent of 32 degrees, it will give me a value there of 11.25. Let's go to two places after the decimal on this one. We'll call it about 11.25. So our side A here is about 11.25 units. Whatever units we had for B, it's going to be the same units for A. We can find C. We can do a similar thing to find C. C is the hypotenuse, and I know the adjacent side, the hypotenuse and the adjacent side. So the hypotenuse and the adjacent side is cosine. I know that the cosine of 32 degrees is the adjacent side. So 18 divided by the hypotenuse, 18 over C, would give me the cosine of 32 degrees. And so I'm trying to solve for C. I'm trying to find C. So let's multiply both sides of this equation by C. And then I'll get C times the cosine of 32 degrees is equal to 18. And so if I want to get C by itself, I'm going to divide both sides by the cosine of 32 degrees. Divide by the cosine of 32 degrees in there for C. And then we'll go to the calculator and get an approximation from our calculator. 18, whoops, come back here. 18 divided by the cosine of 32 degrees. I'm in degree mode, so it's going to automatically assume that that value is in degrees. And we get 21.23. 21.23 for the value for C. Would be 21.23, whatever units again we have. It's going to match whatever units we used for 18. If 18 was 18 miles, then this would be 21.323 miles in there. If it was 18 centimeters, then I'm looking at 21.23 centimeters in there. So there's A and there's B, or angle C. I already know, or side C. I already know angle C is 90 degrees. And of course, you can also find angle B because I know that the sum of angles in a triangle is 180 degrees. I've used up 90 of them already with C, so I've got 90 degrees left to find B. 90 minus 32 is 58. So angle B would be 58 degrees in there. So we can find the missing sides in there of our triangle. All right. So it's always a good idea when you're solving a triangle, work off a picture. It's usually very helpful to do that. Let me grab this thing here. Let me grab that triangle and let's move it down here so we can solve it. Come on, keep moving. Okay, there we are. Let's move it over there. Okay. So here's another triangle. I've got W, big W is the right triangle, and then I've got angles R and T in there. And suppose if I'm told that, get me a pen again here instead of a grabby thing. Let's say that angle R is 48 degrees, and let's say W. How about W is equal to let's give a value there of 67. So angle R is 48 degrees, and W is side W is 67 units long, whatever units you want to use there. So what I want to do is I want to find the other values. I need to find side R, side T, and angle T. Let's do with angle T first. That might be the easiest one because I know that the sum of the angles is 180 degrees. 90 of those are being used with angle W, so that leaves me 90 degrees left over for R and T, and so I need something like 42 degrees if my math is correct. 42 plus 48 makes 90, plus the other 90 degrees for angle W. That fills out our right triangle in there. Okay, and so if we need to find the values there. Let's stay with angle R. Generally, I always like to use the values that were given in the problem if I possibly can. I mean, I calculated T, but if for some reason I made a mistake in calculating T, it's going to throw off all my other answers. So I prefer to work back with the problems that the numbers that were given in the problem if I can. You can't always do that, but ideally that would be what we'd want to do. So W is equal to 67, and W is the hypotenuse. So we've got the value of the hypotenuse. If I'm looking at angle R and I'm trying to find, how about let's find side R to start with. Side R is the angle is the side that's opposite angle R. So if I'm looking at side R, that's going to be the opposite. And if I have the opposite and the hypotenuse, then I know I want to know that use the sine function. So the sine of 48 degrees is the opposite side. It's going to be R divided by the hypotenuse divided by 67. R over 67 is equal to the sine of 48 degrees. I can solve for R. I want to get rid of the divide by 67. So let's multiply both sides by 67. And we'll get that R is equal to, as an exact answer, 67 times the sine of 48 degrees. But we could get a nice approximation of that off of our calculator. Jumping over to Desmos here, I want to do 67 times the sine of 48 degrees. And I am still in degree mode. Always a good idea to check that you're in the proper mode. You know, at some point during this quarter, I would almost guarantee that every single one of us is going to make a mistake because our calculator is in degree mode when we want it to be in radian, or in radian mode when we want it to be in degree mode. But 49.79 would be the length of side R. 49.79 units would be the length of side R. And then if I want to find T, again, I'm going to stick with angle R. And T is the adjacent side. It's next to R, but it's not the hypotenuse. So I know that the cosine of 48 degrees is going to be the adjacent side, T, divided by the hypotenuse, W. So I know that cosine of 48 degrees is equal to T divided by 67. So T would equal 67 times the cosine of 48 degrees. And so let's jump over to the calculator and find an approximate value there. 67 times cosine of 48. Yep, we're still in degree mode. Is 44.83. 44.83 should be our value there. 44.83. Okay. Units, whatever units that I have there, should be approximately equal. It's not exactly equal. It's a good approximation in there. Okay. And well, we are in a right triangle. As a side note, and I could have used the Pythagorean instead of using the cosine theorem, but I should know that this should meet the Pythagorean theorem. So 44.83 squared plus 49.79 squared should equal 67 squared, according to the Pythagorean theorem. The squares of the two sides added together should equal the square of the hypotenuse. Let's go check that over here on our calculator. 44.83 squared plus the other number was 49.79 squared equals this 44,488.773. So let's take the square root of that previous answer there. There, I can do previous answer button. I got a previous answer button that I can pull up there. And if I find the square root of that, I'm getting really close. I'm getting 66.998. I'm not getting exactly 67 because I've rounded off. The 44.83 and the 49.79 are rounded values. They're not perfect. And so when I do the Pythagorean theorem, I don't get exactly 67, but I think I'm close enough to convince myself that my values for r and t must be correct because we satisfy the Pythagorean theorem in there. So we don't get exactly 67 because I've rounded off my r's and my t's. But there I've solved this right triangle. I found all the missing values. And that's one of the very useful things about trigonometry is using it to find missing sides of triangles. All right, and so far we're just working in right triangles. Eventually we'll find some more methods to work with triangles that aren't right triangles. But for now we're looking in right triangles and the right triangle definition of sine, cosine, and tangent.